In this video, you will learn about logarithmic functions and their application. So first off, what is a logarithm? Well, a logarithm, by definition, is an exponent. And that definition is going to be crucial to the study of this lesson because this will explain how we work with logarithms. All right, so another way of expressing this is that y equals log base b of x if and only if x equals b to the y power. All right, it's kind of wordy and it's maybe difficult to understand with the math notation. Let's explain how this works. All right, so what this is basically another way of writing an exponential function. So here is an exponential function. We can write this exponential function as a logarithm over here. So let's try practicing some of these. So here on the left side, we have expressions written in exponential form. On the right side, we're going to convert these into logarithmic form. And it's important to know how to go back and forth between the two. So it's basically just pattern recognition. All right, so here, the way we write this is we write log, and then notice here the base is a 2. So we write the logarithm with a base of 2. And then we're going to put a number next to it in a second, but our definition, we said that a logarithm is an exponent, or in other words, a logarithm is equal to the exponent. So notice the exponent was 3, 2 to the third power is 8, so the logarithm is equal to the exponent. And then the other number, the 8, would go right here. So we have taken the exponential form and we rewrote it in logarithmic form. So it's basically just, again, recognizing the pattern. So try the next one. See if you can get 2 to the 4th power equals 16 into logarithmic form. All right, well, when you do this, it's going to be log, and then we have a base 2. So the base of the logarithm is a base 2 as well. And by the way, that's a subscript. It's written a little bit smaller and below the regular letters and numbers. And then the 16 goes right here, and the 4 goes over here. Because a logarithm is an exponent, so it's equal to the exponent, is equal to the number 4, the exponent. Okay, let's try 2 to the 0 power equals 1. Okay, this would be log with a base of 2, and then it's equal to the exponent, which is 0, and then the 1 goes over here. So we have log base 2 of 1 equals 0. And let's try one more example. So here we have 2 to the negative first power equals 1/2. To write this in logarithmic form, we would have log with a base of 2, because the 2 is the base over here. The log is equal to the exponent, because a log is an exponent, so it's equal to -1. And then the 1/2 would go right here. So again, we can take any exponential expression, any exponential equation like this, and convert it into a logarithmic expression. And vice versa, we can take a logarithmic expression and rewrite it in exponential form. So make sure that you can go back and forth between the two. Now a little more conversation with a logarithmic and exponential function. Okay, these are actually inverse functions. And we learned in a previous lesson that if you take the composition of two inverse functions, okay, we'll always have it equaling to x. All right, and we're going to find that to be true. So here, if we have g of x equals b to the x power, so that's an exponential expression, and f of x equals log base b of x. Because these are inverse functions, when we take the composition of those two functions, so for example, g of f of x, we're going to have it equaling to x, right? Because if we have f of x here, replace that with the f of x function, log base b of x, you put that right in there. So we have g of log base b of x, and what that means is we put that in place of x in the g function right here. So if you have b to the log base b of x power, that will equal x because those are inverse functions. And we'll explain more a little bit how to determine that to be true. but for now it will suffice to say that they are inverse functions, so they will equal x when you take the composition of them. And the other way around, if we do f of g of x, okay, that's going to equal x as well. So we can replace g of x here with the g of x function, b to the x power. And what that means is in the f function, we replace the x with b to the x power. So we have log base b of b to the x power. And again, we can just assume for now that it's going to equal x because we're stating the fact that those are inverse functions. And again, later we will discuss on how to determine that to be true. All right, so those are inverse functions. And let's go back now to converting between logarithmic form and exponential form. All right, so you can get some practice with this. So here we have log base 7 of 49 equals 2, and you're trying to write this in exponential form. So how would you do that? So it's going the other way. So here is the base. So the base in exponential form would be a 7. A log is an exponent. It's equal to the exponent. So 2 is the exponent. And it's equal to, and the 49 goes over here. So this logarithmic equation can be written as 7 squared equals 49. We'll do a few more examples on this slide to get some practice with these, and feel free to try these on your own to see if you can do this by yourself. All right, example 2, we have log base 7 of 7 equals 1, and you are told to write in exponential form. So again, what you do is you take this number, that is the base, so we have 7 as the base. A log is an exponent, so it's equal to the exponent, so 1 is the exponent, and that's equal to this other 7 right here. So that can be stated in exponential form as 7 to the first power equals 7. Here's a third example. Log base 10 of 0.01 equals negative 2. All right, so again, the base is 10, so we can write 10 as the base of the exponential equation. A logarithm is an exponent, so it's equal to the exponent. So negative 2 is your exponent. And then we have it equal to this number right here, which is 0.01. So in exponential form, we can write this as 10 to the negative second power equals 0.01. Here's another example. We have log base 7 of the square root of 7 equals 1/2. How would you write this in exponential form? So the base we see is a 7, so 7 is the base. A logarithm is an exponent, so it's equal to the exponent, so the exponent is 1/2, and that's equal to this other number over here, which is the square root of 7. So we can write that as 7 to the 1/2 power equals the square root of 7. Okay, let's try one more. Here we have log base 3 of 1 over 27 equals negative 3. So again, to write in exponential form, we can take the base of 3, and then the exponent is what the log is equal to. That's negative 3. That's equal to the 1 over 27. So we have 3 to the negative third power equals 1 over 27. So this was giving some practice with converting from logarithmic form into exponential form. Now let's give you some practice with converting the other way, from exponential form into logarithmic form. Here we have 8 to the 0 power equals 1, and you were told to write this in logarithmic form. So what we do is we take log, and then 8 is the base, so the 8 goes down here. A log is or equals the exponent, so it's equal to 0, and the 1 goes right here. So we can write that as log base 8 of 1 equals 0. Here is another one. We have 8 to the negative 1/3 power equals 1 over 2. So to write in logarithmic form, we would take log, and then 8 is the base, so put 8 down here as the base of the logarithm. And a log is or equals the exponent, so it's equal to the negative 1/3, and then the 1/2 goes right here. So we have log base 8 of 1/2 equals negative 1/3. Here is a third example. we have 6 to the 3/2 power equals 6 times the square root of 6. And you were told to write this in logarithmic form. So here we have log, the base is 6, so 6 is the base of the logarithm. And a log is an exponent, so it's equal to the exponent, which is 3/2. That goes over here. And then the 6 times the square root of 6 would go right here. So in logarithmic form, we would have log base 6 of 6 times the square root of 6 equals 3/2. Let's try two more for practice. Here we have 10 to the negative first power equals 0.1, and you were told to write in logarithmic form. All right, so here we have log, and then 10 is the base, so put the 10 as the base of the logarithm. A log is an exponent, so it's equal to the exponent, which is -1, and the 0.1 goes right here. So we can write that in logarithmic form as log base 10 of 0.1 equals -1. Okay, let's try one more. Here we have 81 to the negative 3/4 power equals 1/27. And to write in logarithmic form, we would have log, and then 81 is the base, so 81 is the base of the logarithm. A log is an exponent, so it's equal to the exponent, which is -3/4, and then the 1/27 would go right here. So in logarithmic form, we can write this as log base 81 of 1/27 equals -3/4. Okay, next we want to talk about properties of logarithms. So we have a couple to go through here. The first one is log base b of b to the k power will always equal k. All right, so if you have this where you have these two numbers are the same, and this number is raised to some exponent, it will always equal the exponent. And what that would look like, for example, is something like this. We have log base 3 of 3 to the 10th power. Because the base and this number are the same, your answer is going to be the exponent. It's going to be 10. Which would make sense if you think through this here. If you convert into exponential form, the base is 3, so we have 3. And then a log is an exponent, so it's equal to the exponent, which would be 10. And then that's equal to this part right here, the 3 to the 10th power. So that's a true statement, and the only way that is true is because it's equal to 10 over here. Right? If that was something different, then that would not be true. All right, so if you see the situation, the exponent will be your answer. Now the second property is if you have log base b of b, that will always equal 1. So if these two numbers are the same, it will always equal 1. So for example, if you have log base 4 of 4, that will always equal 1 because these are the same number. And we can verify that because if you convert into exponential form, the base is 4, the exponent is 1, equals this number here. 4 to the first power does equal 4. So the only way to make this true is if this number is 1. So if these two are the same, so 4 and 4 or 5 and 5 or whatever, that will always equal 1. The third property is log base b of 1 will always equal 0. So if we have a 1 here, okay, if that's a 1, your answer will always equal 0. For example, if we have log base 7 of 1, that equals 0 because if we convert into exponential form, 7 to the 0 power equals 1. Right? So anything to the 0 power is 1. So if this number is 1, the only way to get 1 is if 0 is your exponent. So if this number is a 1, your answer will always equal 0. And the fourth property goes back to the composition of the functions, realizing that logarithms and exponential functions are inverse functions. So here, if we have b to the log base b of n power, that will always equal whatever this number is, will always equal n. And that's because we have an exponent or exponential expression, b to some power, but then taking the log of that expression will undo what the exponential function did. So those will basically cancel each other out because those are inverses. and that would give you n as your answer. All right, so if you see that, where we have the base of the exponential expression and the logarithm to be the same, that will always equal whatever that number is. So for example, if we have 2 to the log base 2 of 5 power equals, and you're trying to figure out what that's equal to, that will be equal to this number right here, because the bases are the same. Those will undo each other, and you're left with 5 as your answer. Now for the next part of the lesson, we are going to discuss evaluating logarithms. So we're going to explain to you how to do this, and then we're going to give you some practice problems to try on your own if you want. All right, so here we have, for example, log base 6 of 36. And you were told to evaluate or figure out what is that equal to. So here, if you have something like that, what you can do is you set it equal to x, because that's what we're trying to figure out. We're trying to figure out what is it equal to. It's equal to some unknown number. And then from here, we can convert this into exponential form. So this would be 6 to the x power equals 36. And then we can figure out what is x equal to. And we can do that by making this right side so that it has the same base as the left side. So 36 is the same thing as 6 squared. So once the bases are the same, the exponents must be equal. So x would equal 2. And that one would be simple enough to probably do in your head instead of going through that last step or two. We know that 6 to the second power is 36, but that process will be important for more difficult ones. All right, let's try another example. This one is the same level of difficulty as the first one, but see if you can do this one on your own. We have log base 2 of 16, and we are told to evaluate. So again, what we do is we set it equal to x, and then convert into exponential form. So we'd have 2 to the x power equals 16. And then to figure out what is x equal to, we can convert 16 on the right side to be 2 to some power, so it matches the left side. Well, 16 is 2 to the 4th power, and now here the left and the right side both have the same base, so therefore the exponents must be equal. So x would equal 4. All right, let's try another one. Log base 5 of 25. What is that equal to? So again, we can set it equal to x, convert into exponential form. So we'd have 5 to the x power equals 25. And then 25 is the same thing as 5 squared. And now the bases are the same, so therefore your exponents must be equal. So x would equal 2. So therefore, log base 5 of 25 would equal 2. And I should have stated that as well earlier, is that whatever x is equal to, that is your answer for the original problem. So like log base 2 of 16 would equal 4, log base 6 of 36 would equal to 2. So if you're told to evaluate, the first one would be 2, second one is 4, and the third problem is 2. Let's try a couple more. Here we're going to increase the difficulty a little bit. And for the fourth example, we have log base 4 of 1 over 16. And you're told to evaluate. So to figure out what it's equal to, we can set it equal to x and then convert into exponential form. So to do that, we would have 4 to the x power equals the 1 over 16. And then this right side, we need to write with the same base as the left side. So we want to have this on the right side to be 4 to some power. Well, 16 is 4 squared, so we have 1 over 4 squared on the right side. And then we want to get rid of the fraction, and we can do that by writing 1 over 4 squared with a negative exponent. We can write as 4 to the negative second power. So now the bases are the same, both have a base of 4. That means the exponents must be equal. So x would equal negative 2. So therefore, log base 4 of 1 over 16 is equal to negative 2. Let's try another one. Here we have log base 10 of 100. Well, to evaluate this one, we can set it equal to x and then convert into exponential form. We would have 10 to the x power equals the 100. And the right side, 100, is 10 squared. And now the bases are the same, so therefore we can write or set the exponents equal to each other. So x would equal 2. So log base 10 of 100 would equal 2. Let's do one more. Here we have log base 2 of 8 times the square root of 2. All right, so to evaluate this one, again, set equal to x, and then convert into exponential form. So we'd have 2 to the x power equals 8 times the square root of 2. And this one's a little trickier because we have a square root on the right side. But what we want is to have the same base. We want the right side to have 2 to some power. Well, 8 is the same thing as 2 cubed. So 2 to the third power. And the square root of 2 is the same thing as 2 to the 1/2 power. All right, and then when you multiply on the right side, we would add the exponents, 3 plus 1/2, and that would give you 3 and 1/2. So we have 2 to the x power equals 2 to the 3 and 1/2 power. So because the bases are the same, the exponents must be equal. So x must equal 3 and 1/2. So log base 2 of 8 times square root of 2 would equal 3 and 1/2. So we've talked a lot about converting between the two forms, between logarithmic form and exponential form. And now we're going to switch gears and we're going to talk about the graphs of logarithms. So we stated at the beginning of the lesson that a logarithmic function is the inverse of an exponential function. So for example, if we had f of x equals log base 3 of x, and you were told to graph this, okay, one way we can do this is we can graph the exponential function of this, and then we could reflect it across the line of y equals x. So we're going to work with this graph and do this by hand, and then also we're going to show you how to graph with a graphing utility. So if you take the inverse of this function, we would have y equals log base 3 of x. Then you switch x and y to have x equals log base 3 of y. And then you have to solve this for y. So convert this into exponential form. We would have 3 to the x power equals y. So this would be the inverse. This is the inverse of the logarithmic function. And we can graph this. We've done this before, where you can plug in a value for x to get some output for y. So if you plug in, let's say, -1 for x, we would have 3 to the negative first power, which would be 1 over 3. So that would be 1 point for this function. And then if we had x equaling 0, we have 3 to the 0 power, that would equal 1. All right, so we have the point 0, 1. And if you plug a 1 in for x, we'd have 3 to the first power, which would be 3. And so if we get 3 points, that's kind of enough to know what's happening. We plot those 3 points, we know it's going to be a curve, and we know it's going to be asymptotic to the x-axis, meaning it will never reach the x-axis. And that's because it doesn't matter what we plug in for x, okay, we're never going to get 0 back out. So there's no power to raise 3 to get 0 as an output. And that's why it's asymptotic to that x-axis. All right, and then if we wanted, we could reflect this across the line of y equals x, where basically you switch the x and the y value for each of the points that we had up here. So instead of -1, 1/3, we would have 1/3 and -1. And instead of 0, 1, we would have 1, 0. And instead of 1, 3, we would have 3, 1. And you plot those points, and we connect those points with a curve, and we're going to have this graph right here. So this new graph is going to be the logarithmic function. And we notice how those are inverse functions with the graph because it is reflected across this line of y equals x. And we can verify those points with this right here. If we had y equals log base 3 of x, we can convert that into an exponential function. We'd have 3 to the y power equals x. So if you plug in something for y, so say you plug in a -1 for y, okay, we have 3 to the negative first power, which is going to be 1/3. So x would be 1/3 when y is -1. And that was this point right here. And you can do that for all these points. If you plug a 0 in for y, we would have 3 to the 0 power equaling 1. So x would be 1 when y is 3, or when y is 0. So we have the point of 1, 0, and we see that one graphed right here. And then same thing for the third point. If you plug in a 1 for y, so plug in the point 1 for y, then you have 3 to the first power, which is 3. So that point right here is the point of 3, 1. So we verified that, again, a logarithm and an exponential function, those are inverses of each other. Now at this point, I'd also like to discuss briefly on how to use the graphing utility to graph a logarithmic function. Now keep in mind that you could graph on a calculator, you can graph on your computer with some sort of program, or you could even graph online with different. So what we have chosen to use is a website called Desmos, desmos.com. And this is awesome because you can just type in what you want to graph and it shows it right to you on your computer. So for example, let's say we wanted to graph y equals log base 3 of x. We do log underscore 3 and then x. So we have log base 3 of x right here as our graph. So this can do basically any base and just graphs it right for you. Now what happens if you make some adjustments with the logarithm? So for example, what if we wanted to do y equals log base 3 of, and we do x minus 4. Well, notice this minus 4 shifted the graph over 4 to the right in the positive direction. We're going to find that to be true. And that is if whatever is inside of here, inside of the parentheses, it's going to shift the graph horizontally, and it's going to be in the opposite direction of the sign of the number. So if it were a positive 4, for example, so notice right here it shifts it in the negative direction 4 over to the left. So whatever's in parentheses will shift it horizontally like that. Now what if we were to take x and then we were to, let's put 2 plus that. So 2 plus that logarithm. So if you add something to the logarithm, so not in parentheses, notice what's happening is the graph is being shifted up 2. So right here we have the point 1, 0. It's being shifted up here to 1, 2. All right, so everything's shifted up 2 with that number being added outside of the parentheses. So adding a number on the outside of the logarithm, that is a vertical shift. So a positive 2 shifts it up 2. If you put a negative 2 here, notice how it shifts it down 2. All right, we can do a combination of that as well. So if we had, let's say, negative 3, so sorry, negative 3, and then plus log base 3 of x minus 2. So the minus 2 in the parentheses shifts it horizontally to the right in the positive direction 2. So it goes over 2, and then this minus 3 is a vertical shift. It shifts the graph down 3. So it goes to the right 2 and down 3 from the original graph. And we see that to be true. This point here is 1, 0. If we go 2 to the right, that takes you to 3, 0. And then down 3, 1, 2, 3. That takes you right here to this point. It's hard to get right on it. 3, negative 3. And we can type that in here if we want to verify. The point 3, negative 3 is right on that graph. All right, so again, that negative 2 shifted to the right 2, and negative 3 on the outside was a vertical shift, shifting it down 3. Now, what happens if you were to take the same logarithm? So we have log base 3 of x, but let's say we multiplied by something. Let's say we multiplied by 1/2. Or actually, let's make it a smaller fraction. What if we did like 1/10? Maybe it's too big. 1/3. Well, notice how it makes it, it compresses it so it doesn't go up as far. So it's compressing it vertically, so it's not going up as high. All right, we find that to be true when you do that. All right, it's going to make that happen. And then what if you had like a 4, something bigger than 1? Well, notice it stretches it out, so it goes up here further, and that's what happens when the number is bigger than 1. Even a 2 would do that. All right, so those numbers, if it's a fraction, it compresses it. If it's a number bigger than 1 being multiplied, it kind of stretches it out further. Now, last thing, what if we have a negative on the outside? So negative times the log base 3 of x. Well, the negative, notice how it reflects it across that x-axis. So if it's a positive, so like log base 3 of x, this red graph, it's going to be an increasing function. It goes higher and higher to the right as x gets bigger. And then the blue one, if it's a negative on the outside, then it's going to be a descending function as we see here. Or a decreasing function, because it's going down as x gets bigger. All right, so be aware of what those different things do to the graph. And now I guess let's do one other thing. What if we put a negative x here? So we have log base 3 of negative x. So if you do it like that, it's going to reflect it across the y-axis. All right, so if you put a negative x there, okay, it's going to reflect across the y-axis, and it's going to go like that. Now, a couple other things I want to point out with the graph of a logarithmic function. First is that the function is 1-to-1, because notice, as we see here, this function is passing the vertical line test and is passing the horizontal line test. So because of that, this function would be 1-to-1. Notice the domain as well of this function. The domain would be all our positive numbers. So any real positive number. So notice it's not any negative numbers. And then the range of this function, notice that the range could be anything. So we see here it keeps going down forever and ever. So it can go down into any negative number, and then over to the right, it's going to keep going forever. And it's going to keep going up and up slowly, but it's going to keep increasing more and more. All right, so the range would be all real numbers. Another thing with this graph, without any shifting happening, okay, the x-intercept would be at the point of 1, 0. All right, so it's going to cross right here at this point, 1, 0. All right, and then also it's going to go through the point of B1, So notice here the base 3. Okay, it's going to go through the point of 3, 1. And we see that to be true. If you go over 3 up 1, right here, notice it's going through that point as well on the graph. That will always be the case. It'll go through whatever the base is, that number, comma, 1. That would be another point on the graph. Now, as we were looking at the graphs of the logarithms, we discussed that the domain must be positive real numbers. So the values for x are values where x is positive. So, for example, if we had log base 3 of x, and you were asked what is the domain, we know that this right here, that part, must be greater than 0. It must be positive. So the domain of that is x is greater than 0. Now what if we had log base 5 of x minus 2? Well, the domain of this is where x minus 2, this part, is greater than 0. So if x minus 2 is greater than 0, that means x is greater than 2. So the domain of that function would be x is greater than 2. Here's a third function. We have f of x equals log base 7 of the absolute value of x plus 5. And you were told to find the domain. Well, again, we know this right here, the absolute value of x plus 5 must be greater than 0. And if you can't do that in your head, what we can do is we can break this up. We can set this as two different inequalities. So we have x plus 5 is greater than 0. And then or, because greater than means we have an or statement. Then we have x plus 5 is less than 0. So we solve each of these. We have x is greater than -5 or x is less than -5. So in other words, x can be anything except for -5. And that's going to be your domain. So we can write that as x is not equal to -5, meaning it can be anything except for that value. Now another thing to be aware of is what we call common logarithms and natural logarithms. Common logarithms are logarithms that have a base of 10. So for example, log base 10 of x is a common logarithm. Now a lot of the calculators that you'll see, the cheap ones at least, they can only do base 10. So if you have a calculator, you would see a log button. So if you have a cheap one, it's going to be looking like this. So on your calculator, if you type in log of something, so say log of 10 or 20 or whatever, your calculator is doing a base 10. So log base 10 of x would be also written as log of x. So if the base is not written, it's an assumed base 10. So if you were to write log of 100, that is an assumed base 10. So you could write it there, but it's not necessary. And then to evaluate, you can do that. We'd have 10 to the x power equals 100, and x would equal 2. And in a moment, we'll show you how to use a calculator to type in some sort of logarithm. And then the other type we have is called a natural logarithm. A natural logarithm has a base that is the natural exponential. So that is the letter e. So e is an irrational number, kind of like pi. And that is approximately 2.718. Oh, I can't write. Okay, 2.718, etc. That keeps going forever. All right, so if it's got a base e, that's called a natural logarithm. And the quicker way of writing that is instead of writing log base e, we can write ln instead. So ln, I guess, is like natural logarithm. So when you see that, this is an assumed base e. So if you were told the natural log of x equals 4, and you were told to evaluate for x, you would have an assumed base e, and to write an exponential form, you would have e to the 4th power equals x. And then you can type that in your calculator to get some actual number answer. So again, a natural log has an assumed base e, and e is the irrational number of 2.718, etc. So if you take a look at a calculator, here we are on Google Calculator. Just type in calculator into the search bar. Here we see a little calculator we can use to evaluate or calculate different logarithms. So your calculator could be an actual physical calculator, and what you're looking for is this log button and ln button. So if you want to do like the log of 100, for example, some calculators, each one's a little different. Sometimes you have to type logarithm or push the log button first. So here we do log of 100. We said that was 2, right? Because 10 to the 2nd power is 100. But some calculators, you have to push 100 first. So you type in the number first, and then you push the log button. So each calculator is different. Make sure you know how to use your calculator. But that's all you do. So this button here is an assumed base 10. So log base 10 of whatever you want, and that'll give you your answer. And then right here, ln, so it's an L, not an I. ln, you can type in whatever. So ln of, say, 9. Press enter, and that gives you 2.19, etc. All right, so that's all you do. You just type in or push that button, and then type in whatever you want after that, and that will give you your solution. So the main thing is make sure you can find those buttons on whatever calculator you're using, whether it be online or an app or whatever. Make sure you can find that button, and make sure that you know how to use your calculator, if you should type the number in first or after you push that button. Now to finish off the lesson, we want to talk about some applications of logarithms. So there's many different applications of logarithms. One is with the pH scale for determining if something is acidic or basic. We also have the decibel system for sound. That is a logarithmic scale. We also have the Richter scale for measuring earthquakes. So all of that are just a few applications of logarithms. And so here we have our example, and this is dealing with the pH scale. All right, so here it kind of explains a little bit about the pH scale if you're not familiar with it. So it's saying what the formula is. So the pH level is found by doing negative log of H positive, where H positive is the hydrogen ion concentration measured in moles per liter. All right, so if you have that number, you just plug it in and it'll give you the pH value. And if the value is less than 7, then the solution is acidic. If it's got a pH value greater than 7, then the solution is going to be basic. And then if it's got a pH of exactly 7, such as pure water, then those solutions would be neutral. So what we're doing here is you're testing apple juice, and you find the hydrogen ion concentration is 0.0003. We're trying to find the pH value and determine whether the juice is basic or acidic. So what you do is you plug in 0.0003 in place of H positive right here, and that will give you your solution. All right, so we take that formula, we plug in the 0.0003 right here, and then on your calculator, you just type that in. So you push, it's a base 10, right? So you push the log button, and then you push 0.0003. So just the way we showed you with the Google calculator. And that's going to give you a negative 3.5229. And then just change the sign. So take the opposite of that. That gives you a positive 3.5229. So the pH level of the apple juice is approximately 3.5, and that means that the apple juice is acidic because it has a value of less than 7. And then the second part of the problem says that you also test some ammonia and determine the hydrogen ion concentration to be 1.3 times 10 to the negative 9th power. All right, so if you're trying to find the pH level of that, you put that in place of H positive right here. So you type that in your calculator, take the logarithm of that, and then change the sign. So take the opposite of whatever you get. And if you do it all correctly on your calculator, you're going to get 8.8861. So you've determined that the pH level of ammonia is approximately 8.9. And because that has a pH level greater than 7, that means ammonia is basic. So again, the pH scale is just one of many applications of logarithms. And that concludes our lesson for today. We will see you next time.